This video contains the solutions to section 2.1 worksheet number 1. This section is all about finding areas between curves, and so when we want to do that, the type of integral that we need to set up to do that looks like the integral from the start of the area to the end of the area, and we're integrating the top function minus the bottom function with respect to our variable. Now, in most problems, we have to do some work to figure out where does the area start, where does it end, which one's the top function, which one's the bottom function. But in this one, they actually give us all of that information. We're told that it's bounded above by 16 minus x squared, so my top function is going to be 16 minus x squared. Bounded below by y equals x plus 1, so my bottom function is going to be x plus 1. And then from x equals 1 to x equals 3, so my start value is going to be 1, and my end value is going to be 3. So the area that we're looking for is the integral from 1 to 3 of 16 minus x squared, that's my top function, minus, now the second set of parentheses is extremely important. We want to make sure we're subtracting the entire bottom function, not just putting a minus sign in front of the x and then forgetting to carry that through to the plus 1. So this set of parentheses here, those parentheses are important. All right, now we've just got an integral to do. So we're integrating from 1 to 3. If I distribute that negative, I've got 16 minus x squared minus x minus 1. So if we had forgotten those parentheses, that would be a plus 1, and we wouldn't be getting the right integral. Collecting some like terms, I've got 15, because 16 minus 1 is 15, minus x squared, just putting things in power order there. When I integrate, I get 15x minus 1/2 x squared minus 1/3 x cubed. We've got to plug in 1, plug in 3, and subtract. And when we plug in 3 and plug in 1 and subtract, we end up with 52 over 3. So that's the area that we're looking for in this problem. Here's an example where they give us a picture of the region, which helps us get some of the information that we need. Remember that what we're trying to do is set up an integral where the lower bound of the integral is the start of the area, the leftmost x value of the area. The upper bound is the end of the area, the rightmost endpoint of the area, and then we've got the top function minus the bottom function. So from the picture, we can tell that this line, 3x minus 4, that's going to be the top function, and this parabola, x squared, that's going to be the bottom function. But what this picture doesn't exactly tell us, we can kind of estimate it from the picture, but we want to actually know what the actual values are, is where is this starting point, where is this ending point. Now the way we're going to do that is we're going to set these two functions equal to each other, because what we're looking for is where the two functions cross. So we're setting x squared equal to 3x plus 4. That's going to give us x squared minus 3x minus 4 equals 0. That factors into x minus 4 and x plus 1. So that's going to give us two solutions, x equals 4 and x equals negative 1. And that matches up with what we're seeing in the picture. So that means that the integral that we need is going to go from negative 1 to 4 of my top function, which is 3x plus 4, minus my bottom function, which is x squared. And I'm just going to go ahead and put that x squared in parentheses because it's a good habit to be in, even though in this case, if I had forgotten them, it wouldn't affect my answer. Now we're ready to integrate. Antiderivative of 3x is 3/2 x squared, antiderivative of 4 is 4x, and antiderivative of x squared is 1/3 x cubed. And then we're going to plug in 4 and plug in negative 1 and subtract. In this case, when we do that, we end up with 125 over 6, and so that's the value of this area that we're looking for. So in this example, we're only given the two functions. So they don't give us a picture and they don't tell us which one's on top, where the starting and ending points are. So all of that is going to be stuff that we're going to have to figure out ourselves in this problem. So the best way to do that is get a graph of the region. So these aren't too complicated functions, so we should be able to get graphs of these. Let's look at this parabola first. X squared minus 3x is a parabola. It's got roots at 0 and 3. And since the coefficient of x squared is 1, which is positive, that means that this parabola is going to open up. So this is a rough picture of what that parabola is going to look like. And then if we want to graph this line, that's just y equals 4x. So that's going to be a line that goes through the origin and has slope positive 4. And so that's what that's going to look like. And so now that we've graphed our region, we can tell that the line is going to be on top and the parabola is going to be on the bottom. So as we go to set up our integral, we know that the line function, y equals 4x, should be the first function that we write, and the parabola function, x squared minus 3x, that should be the second function that I write. Now the only thing that's left to figure out are the starting and ending points of my area. Well, we can kind of tell that this is going to be x equals 0 because they both pass through the origin, but we don't know what the other function or what the other point is. And so the way we're going to figure that out is by setting the two functions equal to each other and solving. So we'll subtract 4x from both sides. Remember that when we're trying to solve quadratic equations, we move everything over to one side and then try to factor. We can factor here. We get x times x minus 7 equals 0. That's going to give us two solutions, x equals 0, which we already kind of knew about, but x equals 7, that's the point that we were looking for up here. So 0 and 7. Now we're ready to integrate. So let's collect like terms. 4x minus 3x, that's 4x plus 3x, which is 7x. And then we still have a minus x squared. We take our antiderivative. We get 7 halves x squared minus 1/3 x cubed. We've got to plug in 7, we've got to plug in 0 and subtract. And when we do all that, we get 343 over 6. So in this example, we're given a picture, which is good, but the bad news is that the functions that were being used are a little bit more complicated. So the integral that we have to do will be a little bit more challenging, but that's okay, we can do it. So we see here from our picture that the sine function, which is this curve up here, that's going to be the top of my area, and this line, y equals -1, that's going to be the bottom of my area. So again, when we go to set up our integral, those four things that we need to figure out are the starting point and the ending point, and the top function and the bottom function. So we figured out that the top function is sine of 2x, and that the bottom function is -1. What about the starting point and the ending point? Well, again, we could set these two functions equal to each other, but these functions are going to intersect infinitely many times, so we're going to rely on the picture more here. So we can tell that this is my starting point of my area, and over here, this is the ending point of my area. And if you read the graph, the x-axis carefully, we can tell that this is negative pi over 4, and this is positive pi over 4, positive 3 pi over 4, because this point is halfway in between negative pi over 2 and 0, and this point is halfway in between pi over 2 and pi. And if you ever want to know a number that's halfway in between two other numbers, you add those two numbers together and you divide by 2, you average them. So that's going to be 3 pi over 2 divided by 2, which is 3 pi over 4. And similarly, that's how I figured out negative pi over 4 over there. So negative pi over 4 is my lower bound. 3 pi over 4, that's my upper bound. So my integral is from negative pi over 4 to 3 pi over 4 of sine of 2x plus 1. Now, if that 2 wasn't there, the antiderivative of sine is negative cosine, but the 2 is there. So we would need to do a little simple substitution of u equals 2x. My du is going to be 2 dx, which means I would need to put a 2 in there and a 1/2 out front. So that's going to give me, if I put in my 2 next to my dx and a 1/2 out front, that's going to give me a new integral, which is going to look like 1/2. I'm going to change my bounds in just a second. My new integral is sine of u plus 1 du. Now, what are my new bounds? When x equals negative pi over 4, u is going to be 2 times that, negative pi over 4. So that's going to be negative pi over 2. So that's my new lower bound because I've got a u integral, and so the bounds in this integral should be values of u. My upper bound is 3 pi over 4, and so that's going to mean u is going to be 2 times that, 2 times 3 pi over 4, which will be 3 pi over 2. That's my new upper bound. So I've got 1/2. Now I'm ready to take my antiderivative. The antiderivative of sine of u is negative cosine of u. The antiderivative of 1 with respect to u is u, right? Not x, but u. And then I'm plugging in 3 pi over 2 and negative pi over 2. So I'll actually work this one out for you. I skipped the previous ones because it was just dealing with fractions, so figured you could do those on your own, but let's do this one together. So we've got negative cosine of 3 pi over 2 plus 3 pi over 2 minus the negative cosine of negative pi over 2 plus negative pi over 2, so that's minus pi over 2. Now it turns out that the cosine of 3 pi over 2 is 0, and the cosine of negative pi over 2 is also 0. So all we get in those parentheses there is 1/2, and then we get 3 pi over 2 minus pi over 2. That's 4 pi over 2, also known as 2 pi, but then we multiply that by 1/2, and all we get at the end is just pi. So pi is the area of that region that we're looking for. For this last problem, we're asked to find the region bounded by y equals x squared and y equals 8 minus x squared. So again, here it's helpful to get a graph of this region. So we can graph y equals x squared relatively easily. We know that that's going to look like this parabola, look something like that. And then y equals 8 minus x squared, that will look like a flipped upside down parabola, shifted 8 units up, so that's going to look something like that. And so we can tell that the region that we're talking about is this region in here trapped in between those two parabolas. And we can also tell from our picture that the parabola I've drawn in purple, the 8 minus x squared, that's the upper function. And so we can already set up most of our integral here. We know that it's going to be an integral from a number to another number. We haven't figured that part out yet. But the upper function is going to be 8 minus x squared, and then the lower function is going to be x squared. So now all we have to do is figure out this starting number and this ending number. And as usual, the way we're going to do that is by setting the two functions equal to each other and solving. So we set x squared equal to 8 minus x squared. Add x squared to both sides. That gives us 2x squared equals 8. X squared equals 4. X equals plus or minus 2. So that means our starting number is -2 and our ending number is +2. So there's our setup. Now let's integrate. Before we integrate, we'll do a little bit of simplification. That's going to be 8 minus 2x squared. Take the antiderivative. That gives us 8x minus 2/3 x cubed. Plug in 2, plug in -2, and subtract. So we're going to get 8 times 2 minus 2/3 times 2 cubed, and then minus 8 times -2 minus 2/3 times -2 cubed. Just be careful with all those negatives kicking around. 8 times 2 is 16. 2 cubed is 8. 8 times 2/3 is going to be 16/3. That's 16 minus 16/3. And then minus, in those parentheses, we've got minus 16. And then minus 2 cubed is minus 8. Times minus 2/3 is going to be plus 16/3. So 16 minus 16/3 is 32/3. So that's 32/3 minus 32/3. And so my final answer here is going to be 64/3.